So it turns out this whole idea of what we mean by finding volumes under surfaces, right? That we want to draw the parallel with what we did back in Calc 1. How do you do this, right? And so I mentioned you guys want to kind of think about a Riemann sum. And so the way it's usually defined, integral from a to b f of x dx, is defined to be equal to a limit. Limit as what? Well, limit of what? Limit of this thing called a Riemann sum. A Riemann sum looks like this. It has a function here. And then it has a delta over here. Delta x, okay? And what's usually done, okay, just so you understand the picture, here's your function, f of x, right? And let's say it's defined over the interval a, b, right? So this is the x-axis, let's say, and I want to approximate the area. What do? I build a bunch of what? Rectangles. That's exactly right. So a partition, yeah. We create a partition of the interval, right? And so we're used to that. We go a is x0, that's less than x1, dot, 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 up to xn, and that's b, right? And you get these subintervals. And then what you compute, so if I say, this is x delta xi, right? At the ith subinterval, when I say delta x, I'm really talking about, if this is like the, this could be delta xi right here. Delta xi. And that gives me the width of a rectangle. It's kind of cool to do Calc 1 in like 2 minutes. I love this. We're going to teach you the fundamental theorem, right? And then what do? You want to get the height of the rectangle, and so what do? Yeah. Now you compute f of something, okay? And what our books do different notations. I think our book, if I remember right, they'll like say xi, and they put a little asterisk here or something like that. And what that means is, I don't know how, but somehow pick a value in the ith subinterval. Now, what are some good ideas? Left endpoint, right endpoint, midpoint. And one of the reasons we do left endpoint or right endpoint is if the function is, say, decreasing, and you always pick the right endpoint, you know you're going to get an underestimate. But what happens if you always pick the left endpoint? You get an overestimate, right? But the point is, if I take the limit, I don't care how you picked your point in the subinterval. Oh, limit is what happens. So there's two things that are said, right? Either the number of subintervals goes to infinity or the size of the subintervals goes to 0. And we write the latter. The size of delta goes to 0, the size of the partition. And how do you define that? The size of the partition. That's usually kind of glossed over in Calculus 1. And maybe we'll gloss over it here a little bit also. But I'm going to say something here, okay? Usually what we say is well, whatever the biggest one of these delta xi's is, that's the size of your partition. And the reason, by the way, that taking n to infinity doesn't work is like, what if someone, you might say this is a stupid move, right? But what if someone just said, hey, I'm going to just chop up this interval over and over and over again until I have infinitely many, right? So I'll be really accurate here. But I'm not going to be accurate in terms of the integral, right? So that's why we go with this. But it's also true that if you make delta go to 0, then automatically n is going to go to infinity, right? And Paul, why even bring that up? Well, one of the reasons I bring it up is because actually, when it comes right down to it, you guys have been through Calc 2. Is integrating easy or not so easy?
Okay.
I'm glad you think it's easy. If I just write some function down, do you think I could write one down that you can't integrate?
Yeah.
The answer is yes. Could you write one down I can't integrate? Absolutely. But what I can do is I can put it in my TI-83 and give you a value, because how does TI-83 do it? Like this. It divides it up into subintervals and gives you an approximate, right? I mean, anyone that's going to be an engineer knows that we are approximating solutions, integrals all the time. Anyways, one reason to bring this up is there are some pretty nasty functions that you hit sometimes that are really steep on the ends. And one common technique that's used is you say, well, let me just really divide it up when it gets really steep. So this idea that I'm talking about actually has a practical value at times. Just kind of cool. So anyways, we're trying to extend it to higher dimension today. And I said, this is good for you guys to think about this Riemann sum, okay? And I'm going to show you what the book does, but I'm also going to point out kind of what it doesn't show you, okay? And then we're going to get into more of the details after the test, because that's what you guys want, and rightfully so. We really have to concentrate on getting ready for the test today. But there's some beautiful pictures that kind of show you the idea of how would you do the same thing? I mean, here's a surface, and I want to compute volume underneath, right? Actually, let me get rid of the solid for a minute. Because now, what we can look at is the region R is taking the place of my interval, right? I mean, what I just showed you guys here, right? We had an interval. And by dividing up the interval, then we'll use F to get. So how do you divide up a region R that's underneath the surface, right? Because you'll notice, guys, in the book, let me go back to the top for a second, the double integral, do you see it has an R underneath it? That's what we mean. We mean we want just like I want the area between A and B, I want the volume under the surface but above the region R. Does that make sense to you guys? It kind of gives me a closed, bounded area. And they use R because they're going to say rectangle. Okay? So the idea is, what I'm doing right now is I am showing you pictures in the book to explain the double integral. The double integral over R of f of xy, and then what do we write here? We're not going to write dx anymore. We're going to write dA. dA. Where A stands for what? Area of what? Well, think of the A like our x. This is again, it's a differential, okay? But what is it? Well, let me show you one more thing that kind of shows it. Remember how here's the x-axis, right? We divided AB into n subintervals. Well, what you could also do is you could divide, I'll call it CD for the y-axis, into a different n subintervals if you want, but m and n, I don't know. But what you get then, right, is you're dividing this, you're getting coordinate plane here, right? And then these boxes here, right, here's the solid, right? I can compute f of, I won't show the solid now, see? Again, somehow in each of the squares that you have, pick a point. You with me? So again, trying to extend the idea, okay? So we define this as the limit of a Riemann sum. Namely, it's going to be the limit, and this time your book puts a little p here, and they say as the size of the partition goes to 0. Okay? And we're going to put a sum. And then instead of dA, right, what do I need? I need, well, yeah, I mean, I guess, because if you think about x times y giving you the area of one of these rectangles, right? But let's see what we do, because I think they have a better notation here. Here, they say delta AK. I like that. I like that. It's what I did, right? I did delta XI because for me, there was something I missed up here, guys. I didn't write I equals 1 to n because I told you we're dividing into, I didn't write it, but I said it, n subintervals. N subintervals. So now we're still going to have some number n, right? Let's use k like they do. K equals 1 to n. So then this is the area of the kth subinterval. And then what happens here is somehow, again, take the midpoint of each rectangle or whatever it is you do. You have xk star and yk star or something like that. Somehow you're picking a point that's in a particular rectangle. Okay? Now there's some other added issues that you didn't have in Calc 1 already. Just trying to do this. And these are shown in the pictures a little bit. I mean, well, no, they're not. Not yet. So, well, let me show you. I mean, one issue is this, guys. I showed you a rectangular region, right? What if the region I'm interested in is a curve? Like, let's suppose you want to find, hey, compute the area of the volume of a basketball, right? Well, we have a formula, but where did it come from? It actually came from some of the ideas that we're using right here. Slicing, okay? If you think about, here's my surface, I could actually write that formula. But how would you do a Riemann sum? I mean, I guess what you do is you get a grid, right? So you have this, and then you have this. But do you notice how some of the squares, or rectangles I should say, are totally within R, and some of them are totally without R. They're not in R, so you don't want to count those, right? But what about these ones that are only partly in there? You guys see that? That's an issue. So usually what's done is we only count the squares that are, or rectangles that are totally in my region. Okay? And we will get an inner, so this is sometimes called the inner Jordan, which is another mathematician, content. Okay?
So you're going to shove the areas of the squares down to 0?
Yeah. And so we do that how? Well, by dividing up the y more and dividing up the x more. And as we do that, just like in Calc 1, you're going to get less error, both what you're seeing here and along the z direction. Okay? Now there's one more word that I'm going to go back to Calc 1 for. way at the top. Do you guys remember this word? Sure you do. Integrable. Right? Am I able to compute the integral of something, right? We say f is integrable when this limit, you know what I'm about to write? Exists. That's right. Because we know that sometimes limits don't exist. Okay? This integral that we're defining, whether it's one-dimensional or two-dimensional, as the limit of a Riemann sum, is called a Riemann integral. Now I'm just going to share a little story. I got to graduate school, my first semester graduate school. I was taking analysis. I said, yeah, I took that as a math major. I could do that. And I showed up, and they were using a completely different integral, which they were surprised I'd never heard of. I've heard of the Riemann integral. I didn't know there was another kind. Okay? But I thought I'll share it with you now. There's something called the Lebesgue integral. See, in the Riemann integral, remember I said I don't care how you pick the point, it's going to converge, da 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 da. Matter of fact, back to Calc 1 for a second. This picture here. Why did we pick the right endpoint? Because we wanted an underestimate. If you pick the left endpoint, you get an overestimate. But we said that if it's integrable, that means both of these limits converge to the exact value. Well, it turns out that basically Lebesgue integral, okay, this is kind of a multi-step approach. So the limit exists for more functions. Because just like you guys told me, you can write a function I can't integrate. Okay? That's true. But if I have Lebesgue integration, maybe I can integrate it. It's a different technique. And it is not my job to go into Lebesgue integration today. And I won't. I just want you to know it exists. Like I said, I was blown away. Like, whoa. Okay, question, Aaron?
Yeah, can you use it for cosine squared of x?
You mean cosine of x squared?
Yeah.
No, I don't know. I think so. I think so, because it's really based on the idea of something called lim sup. And so it's almost like, and lim inf. These are words you'd get to later in mathematics. But I guess what I'm saying is Lebesgue integral doesn't depend so much on what the function is. It depends more on functions near it. And so I feel like the answer is yes, but since I wasn't prepared for that question today, I'll have to get back to you. I'm not completely sure, but I think so. Okay, back to our program, guys. What are we going to do with this? We're going to be solving integrals, again, not as limits of Riemann sums, but by iteration. Iterated integrals. I love this sentence. Fortunately, there is a practical method that reduces double integrals to one variable integrals. You kind of do things a step at a time. Okay? And the example I picked today is this one. So, no, let's not do that. Well, here. Consider the function f of xy equals 4 minus 1/9 x squared minus 1/16 y squared. And by the way, the highest point you could possibly get for this function would be, what's the maximum? Yeah, you don't need your calculus to know that the highest this thing's going to get is going to be 4. Actually, the coordinates of the highest point would be 0, 0, 4. I thought this would be a nice example. Okay. So, and actually, if I just think about it in the x direction, right? So if y is 0, what shape is 4 minus 1/9 x squared? Parabola, right? And so I guess if I throw in a 3, I'm down to 3, right? So that, it's coming down in this direction. And here, if I throw a 2, I'm down to 3. So maybe, no, I got to throw in a 4. So it's not quite as steep in the y direction as it is in the x direction, but it is coming down. You guys see that? And so the surface, let me draw the rest of it, kind of in the, this is my x, y, z, right? And so the rest of the surface might kind of be drawn, I'll just draw it like this, because what I'm interested in, here's the problem. I want to find the volume of the solid bounded by the coordinate, I'm going to say planes instead of axes, right? Because you could think of the solid I'm talking about like here's a wall and here's a wall, and then what I'm going to do, guys, is I'm going to move along a certain x value and along a certain y value, and so I get this kind of rectangle, right? So I want to find the volume of this solid. So the coordinate, it's bounded by the coordinate planes, the plane x equals 3 and the plane y equals 2. So like I said, we dropped 1 in each direction there and there. And I'm not sure, well, what point is that? I guess we could compute it, right? If we plug in 3, 2, what's the output at that point right there? 2, right? 3, 2, 2 would be that point. And then 3, 2, 0 is...
Not.
It's not?
No, that'd be 3, 4.
Let me check that again. If I plug in 3 for x, 9 times 1/9 is 1. Oh, you're right. I would need a 4 to get a 2.
Yeah.
I don't have that. All right, so 3, 2, who cares? Let's leave it at that. But it's not 2. Anyways, I want to find this volume. Well, again, R here is a rectangle in our example here, right? So it's going to work out really nicely. R is the rectangle here on the base, right? That's R. Okay. So what we're going to do is the following. We compute as an iterated integral. Here's the idea. I just wrote down I'm going from 0 to 3, and I put a dx over here. I'm also computing dy, the integral 0 to 2. And again, let me throw my function in here. My function was 4 minus 1/9 x squared minus 1/16 y squared. Is this okay? So this is called an iterated integral. Now the way integrals work, we don't write parentheses, but there are kind of inside out parentheses that you never write, or at least I didn't write this time. Okay? And the idea is this. When we say we're going to integrate this function dy, it's almost like this, guys. You are fixing an x value, and you're finding the area under that curve. So see that green slice I just took? If I found the area under that curve, that would be right there. Or if I found the area under the curve in the front, that'd be a little different. It would be less area in the front. Are you with me? But these areas that I could compute by that inside integral change continuously. And so for a nice example like this, you'd expect this to work. You guys remember Calc 2, you did applications of integration. You guys did, remember the disk method and the shell method? You were finding disks and then, right? You were then integrating. Basically, pi r squared, you were integrating. Well, this is the same idea. And so it turns into a double integral. Okay? So let's compute it quickly. What do I get? Well, let me leave the 0 to 3 dx here and work on that integral. So I would say that that's 4x minus, this becomes x cubed over 3, so 1 over 27x cubed minus, this is what? Oh, whoa, 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 whoa. Start over. Hey, great thing is, I'll delete that when it goes to production. 2640. Let's try that again. No one at home will ever know why that suddenly scratched out, but you guys know. All right, let's try that again. So, what I was saying was, we're going to integrate dy with respect to y. Let's write down 0 to 3, and let's write down dx, and let's just work on how would you integrate this dy. So 4 becomes 4y. Question, Sullivan?
Does it matter which one you do first?
That's a good question. Sullivan's asking me, could we integrate 0 to 2 dy after integrating 0 to 3 dx? Sounds like Kathy and maybe a few others are going to try it that way while I do it this way, which is really cool. So that's an interesting question. Does it matter? Anyways, 4y. I hope the answer is no. I hope it doesn't matter. Minus 1/9 x squared y. And then minus, wouldn't this be 1 over 48y cubed? Okay, and I'm evaluating the y's from y equals 0 to y equals 2, right? Because that's what we said we were doing. And so when I do that, let's see what the green turns into. The green turns into, okay, well, first thing, this is a really easy example. When I plug in the zeros for, f of b minus f of a, everything's going to zero out, right? So I'm just going to worry about what happens when I plug in a 2 for y. I get the function 8 minus, this would be 2/9, and you still have an x squared. That stays. And when you plug a 2 in for y, it's 8 over 48, which is the same as 1/6, right? All right, so I'm getting there. Now I need to integrate dx. And so this becomes 8x minus 2 over 27x cubed minus 1/6 x. And again, I'm going from 0 to 3. Boy, did I make this example nice. You plug in the 3, you get 24 minus, you plug in the 3, look what happens. The 27s cancel, so you just get 2. You plug in the 3, 3/6 is a half. I'm getting 21.5 for the volume. That's a pretty nice value. Okay? Now, for the sake of time, I will tell you the other way should also give you 21.5. And either way, both ways, iterated integral gives you the same value that you would get if you actually computed this using limits. Okay? If a function is integrable, you can write it dy dx, or you can write it dx dy. Now, by the way, sometimes one way dy dx might be easier than dx dy, or vice versa. We'll see that later. But if you can compute them, the values will be the same, and it's exactly what we're looking for, the volume under that surface. Aaron?
Can the domain and range, like the endpoints, be put in terms of a function as well?
Yes, because you're right. This particular example is as easy as it can be because everything was flat, right? It turns out that the inside quite often is a function you have to substitute in rather than a number. And we'll see that. And that gets even more complicated in the chapter when we jump to here. Volume, right? So what's this? A triple integral? Well, all that's saying is that if I have a function of 3 variables, you can up it a notch, right? Up it a dimension. What are you computing? Hypervolume? I don't know. But it doesn't matter. We will see that there are very useful applications of triple integrals, work and centroids and, well, other things. The idea of centroids is what's related to average value. You know, you guys were asked to read a little bit about the average value of a function. And I'm almost at break time, so I'm not going to say much today about this. Right? Here's your Calc 1 formula. F bar is 1 over b minus a. Right? This had to do with the mean value theorem, it's called. How would you extend that to the average value of a function in Calc 3? Look what they wrote. 1 over the area of R. Right? So for us, I guess I know the average value of the function, right? In my example. Yeah, this is kind of cool. Here. Right? Because 21.5, right? That's 43 halves, right? So if I want the average value of my function f of xy over our rectangle, all I have to do is take that 43 halves, which we computed, and multiply by 1 over, what's the area of our region? 6, okay? So it's 43 twelfths, which is, well, not 4, but it's more than 3, right? 42 twelfths would be 3.5. So it's a little more than 3.5. Okay, looking at the picture, you can kind of understand that, yeah, you know, this function, the highest point is 4. It stays pretty high unless you go near this corner, then it really dips. But somehow the average value of that function is a little more than 3.5. Okay? So this is, again, extension of Calc 1 idea. And that's all I want to do today, guys. I'd like to go back and help you get ready for your Chapter 14 test. But this is probably a good way for us to...